let's take a look at some properties of the cross product. Previously we showed that three vectors are coplanar if we could express one as a sum of a scalar multiple of the other two. So if I take vector w and express it in terms of a scalar of u plus a scalar of v. Now that we've learned about the cross product, we have a more efficient way of determining whether or not three vectors are coplanar. So what we're going to look at is u dot v cross w. So note we're going to start with v cross w. That is a vector perpendicular to both v and w. So let's draw that here in our diagram. Here is v cross w. So it's perpendicular to v and it's perpendicular to w. If u is in the same plane as v and w, then the cross product v cross w should also be perpendicular to vector u. And if that is the case, then u dotted with v cross w should equal 0. So to prove that three vectors are coplanar, all we need to do is cross two of them and then dot it with a third vector. And if our result is 0, then we know that all three vectors are coplanar. And that's all this will tell us. It will not give us the linear combination shown here. So again, if u is perpendicular to v cross w, then u dot v cross w is equal to 0, and that tells us that u, v, and w are coplanar. So let's go through an example. Determine if a, -1, 4, -7, b, 2, -3, 5, and c, 5, 0, and -1 are coplanar. So let's say we choose to do a cross b dotted with vector c. That means we'll have -1, 4, -7, and we're going to cross that with 2, -3, and 5, and dot it with 5, 0, and -1. If there are no brackets and we have a dot and a cross product involved in an operation, you will always start with the cross product. Alright, so let's determine the cross product, a cross b. So a cross b is going to be 20 minus 21, so that's -1. -14 plus 5, so that's -9. And 3 minus 8 is -5. And then I'm going to dot that with 5, 0, and -1. And if I dot this, I get -5 plus 0 plus 5, which equals 0. So this tells us that a, b, and c are coplanar. We could have also proven this by doing a dot b cross c, and again starting with the cross product, then dotting. Or we could have also done a cross c dotted with b. Any combination of a, b, and c crossed and dotted should give us 0 if they are coplanar. So again, the above example is a more efficient way for determining whether three vectors are coplanar, but it will not determine the linear combination. So if it asks for the linear combination, we need to go back to our previous method. For example, take this linear combination and solve for k and l. The next part we're going to look at are some proofs. So given vector a, b, and c with the following parameters, prove that a cross b plus c is equal to a cross b plus a cross c. We're going to try to prove if the distributive property holds for the cross product. So for our proof, I'm going to start with the left side. I'm going to start with a cross b plus c. Alright, so we already know vector A is A1, A2, A3. And we're going to cross with B plus C. So B plus C would have the components B1 plus C1, B2 plus C2, and B3 plus C3. Using the formula for the cross product, I'm going to end up with A2 times B3 plus C3 minus A3 times B2 plus C2. That's the X component. The Y component will be A3 B1 plus C1 minus A1 B3 plus C3. And finally, the Z component will be A1 B2 plus C2 minus A2 B1 plus C1. So there is our Z component. Next, we're going to expand. So I get A2 B3 plus A2 C3. So I expanded this bracket first. I'm going to do the same thing with this bracket. And this is all the X component. So I get minus A3 B2 minus A3 C2. And then for here, I get A3 B1 plus A3 C1 minus A1 B3 minus A1 C3. And for the Z component, I get A1 B2 plus A1 C2 minus A2 B1 minus A2 C1. I'm going to take all the terms with A and B. So here they are here. Group them together, and then take all the terms with A and C and group them together as well. So here is what I end up with. So let's take all the A's and B's. I have A2 B3 minus A3 B2. Then I have A3 B1 minus A1 B3. And then I have A1 B2 minus A2 B1. And I'm going to separate them from the C terms. A2 C3 minus A3 C2, A3 C1 minus A1 C3, and A1 C2 minus A2 C1. And if you look closely at these two brackets, the first set of brackets is the cross product for A and B. So this is A cross B, all this. And all this here is A cross C. So now we've shown that the left side is equal to the right side, and that the distributive property over vector addition holds for the cross product. So that this up here is true. So I'd like you to work on the following questions from your book first. And then I proved the distributive property, but I'd like you to prove the commutative property using vectors A and B shown here. Prove the associative property using the same vectors, and also prove that A cross A is equal to the 0 vector. So you can use the formula for the cross product and the components and see what happens. I'd like you to prove the following: that A plus B cross A plus B is equal to 0 using the distributive property and the commutative property. Don't use this property here, that would make it too easy. So I want you to use the distributive property first, and then using the commutative property, you should be able to show me that this is equal to 0 as well. Good luck.